Usually when we talk about a map, there is this underlying expectation of absolute precision.
Right. Like it's fixed.
Exactly.
Yeah.
Think about architecture or, I don't know, city planning. You look at a city grid, you see that solid black line, and the cartographer is pointing at the paper, essentially saying, there it is. That's Elm Street. It was there yesterday. It'll be there tomorrow.
Yeah, it operates on this binary reality. You're either standing on Elm Street or you aren't. There's really no ambiguity there.
Right. It's clean.
Mm-hmm.
And frankly, it's comforting. We like things to be static. We want our categories to be rigid. And we want things to be exactly where we left them.
Human nature, yeah.
But today, we're taking a sledgehammer to that static map. Because when you step into the world of quantitative finance, that beautiful fixed blueprint is completely useless.
Completely useless. I mean, we are looking at a landscape that is constantly shifting.
Yeah.
Financial markets are purely dynamic. They're these living, breathing entities driven by literally millions of microscopic decisions happening every single second.
It is the absolute definition of a moving target. And that dynamic reality is exactly what we're going to explore with you today.
It's a fun one.
It really is.
Yeah.
We're going to translate the dense, chaotic mathematics of quantitative finance into a visual, intuitive story. We're looking at a foundational academic lecture, specifically a document titled M1L3.pdf from a Certificate in Quantitative Finance course. And our mission is to decode it.
And decoding is definitely the right word, because when you look at the raw mathematics of how applied mathematicians, the quants, right, how they model these markets, it can feel like staring at an alien language.
Oh, absolutely.
But the underlying logic is just brilliant.
So we are going to unpack the journey from a very simple step-by-step random walk, which is basically, flipping a coin to see where a price goes, all the way up to the elegant continuous mathematics of probability distributions.
Right, with a minimum of fuss, hopefully.
Exactly. We're going to deeply explore each conceptual leap. We aren't just going to read equations at you. We want to make sure you truly understand the why and the how behind the math.
Because if you understand the why, the equations stop looking like a bowl of Greek alphabet soup.
Right.
They start looking like a narrative. I mean, they tell a story about how information flows, how uncertainty grows, and ultimately how money actually moves through time.
So let's lay the absolute bedrock for this entire mathematical universe. Before we can model a whole global financial market, we have to model a single isolated movement.
Yeah, start small.
Right. We're going to build what is called a trinomial random walk.
So to capture something as complex as a stock price or, say, an interest rate, you have to strip it down to the simplest possible representation of change.
Okay.
Imagine a variable. Let's just call it y. This y is our random variable. For the sake of having a picture in our heads, let's say y is the price of a single share of a company.
Okay, got it.
What?
Y is our stock price. And we are looking at this price y at a very specific frozen moment in time.
Right.
The question is, what happens when we unfreeze time? Just for a tiny fraction of a second. We want to move forward exactly one tiny step in time we will call delta t.
Yes, delta represents a microscopic chunk of time. In the real world, maybe it's a minute, maybe it's a millisecond.
Just a tiny tick of the clock.
Exactly. The point is, during that single discrete step in time, our price y has 3 and only 3 possible paths it can take.
Hence the name, right? A trinomial walk, 3 paths.
Precisely. Let's map out those 3 branches. You're sitting at your current value, y. After that small step in time, delta t, the first possibility is that the price goes up.
Okay.
It jumps by a small specific amount, which we'll call delta y.
So if y is $50 and our step delta y is 1 cent, the price goes up to $50.01.
Exactly. And the probability of it taking this upward jump is represented by the Greek letter alpha.
Okay, so path 1 up by delta y with a probability of alpha.
Perfect. Path 2 is the mirror image. The value can go down. It drops by that exact same small amount, delta y.
Right.
And for this foundational model, we assume the market is locally unbiased. The probability of going down is exactly the same as going up. So the downward probability is also alpha.
Now, I want to pause on that assumption for a second. We're assuming the chance of a stock ticking up 1 cent is exactly equal to it ticking down 1 cent. Is that actually realistic, or is it just, mathematically convenient?
It's an excellent distinction, and it's a bit of both. Over the long term, a stock might have a trend. It might drift upward because the company is growing, making profits.
Right, you hope it goes up over years.
Yeah, but when you shrink your perspective down to a microscopic time step, a millisecond, That long-term drift is totally overshadowed by the random noise of people buying and selling.
Oh, I see.
So at the microscopic level, assuming equal probability for an uptick and a downtick is a highly effective approximation.
Okay, that makes sense. The noise drowns out the signal at that tiny scale.
Exactly.
So we can go up by delta E with a chance of alpha, or down by delta E with a chance of alpha. What's the third path?
The third path is that it does absolutely nothing. The price stays completely flat. It remains at Y.
And how do we calculate the odds of it doing nothing?
We use the most fundamental rule of probability. All possible outcomes must add up to 1 or 100%.
Right, you can't have more than 100%.
Exactly. You cannot have a 110% chance of something happening, and you can't have an 80% total chance. If the chance of jumping up is alpha, and the chance of jumping down is alpha, then the chance of staying flat must be whatever is left over from 100%.
So mathematically, that's just 1 minus 2 times alpha.
Exactly right.
Right. You subtract the up chance and the down chance from the total 1. So visually, if you are sketching this on a napkin, you draw a single dot on the left side of the paper. That is our current price right now.
Yep.
Then you draw 3 lines branching out to the right. The top branch slants upward to Y plus delta Y. The middle branch goes straight across, staying at Y. The bottom branch slants downward to Y minus delta Y.
Yeah.
It looks like a 3-pronged fork.
That's the perfect visual. Now imagine what happens when you start layering these time steps one after another. Because the market doesn't just tick once and freeze forever.
No, it ticks continuously. It's
Yeah.
relentless.
Right. So let's say the top branch was chosen on the first tick. The price is now sitting at that new higher value. From that new dot, if we move forward another tiny step in time, there are again 3 branches growing out of it.
Oh, wow. So 1 step gives us 3 possible endpoints. 2 steps give us 9 possible paths. 3 steps give us 27 paths.
Yeah.
It's just an exponential explosion of possibilities.
It is. If you run this process for thousands of time steps and you trace out just one specific path that the price happens to take through that massive web of branches, what does it look like?
I mean, it must be chaos.
It looks like an incredibly jagged, erratic, up and down line graph. It looks like a mountain range drawn during an earthquake. It is full of sharp, unpredictable peaks and sudden, violent valleys. This is the essence of a random walk.
I'm looking at this jagged mountain range in my head, and I have to ask a blunt question.
Go for it.
It looks entirely chaotic. If the path is truly random at every single microscopic step up, down, or flat, then predicting any single specific path from the start line to the finish line seems fundamentally impossible.
It is fundamentally impossible.
Then why are we doing this?
Wow.
If we can't predict a single path, why is this model useful to anyone trying to navigate finance?
And that realization right there is the crucial pivot point in quantitative finance. To build a useful model, we have to completely abandon the dream of absolute prediction.
Okay.
We are not trying to predict the exact price of a stock next Tuesday at 2:04 p.m. We don't care about the single realization.
We're giving up on the individual tree.
Exactly. You're giving up on the tree because we are exclusively interested in the forest. We want to understand the probabilistic properties of the entire system as a whole.
Okay, let's unpack that. What does studying the forest actually look like in this context?
Well, if you run that trinomial random walk a million times, you get a million different chaotic, jagged lines. But if you walk over to the finish line and look at where all those million lines ended up, a remarkable pattern emerges.
Really?
Yeah. Some paths wandered incredibly high, some plunged incredibly low, but the vast majority of them ended up clustering somewhere in the middle. We want to understand the exact shape of that cluster.
Okay.
We want to know the precise mathematical odds of ending up in a certain region rather than guessing the exact final coordinate.
That is a massive conceptual shift. We're moving away from where will this exactly be to what are the odds it will be roughly over there.
Yes.
It's the difference between asking what number will this roulette wheel land on versus if I spin this wheel a million times, what percentage of the time will it be red?
Precisely. And to measure this cluster of probabilities, we need a specific mathematical tool. We need a way to quantify how probability shifts and moves through time.
Right.
This introduces a core concept, the transition probability density function.
The transition probability density function. That is quite a mouthful.
It is.
Mathematically, the source writes it out as a lowercase p, followed by some variables inside parentheses. So it's p of y, t semicolon, y prime, t prime. Let's break down this notation because getting comfortable with the language is half the battle here.
Let's pull it apart. The variables before the semicolon, the y and the t, they represent the current state of the world. So y is our current stock price, and t is the current time on the clock. Think of it as our starting anchor, where we are right now.
Okay, current value, current time, and the variables after the semicolon, the ones with the little apostrophes, the y prime and t prime.
The variables with the primes, the y prime and t prime, represent the future state. So y prime is a potential future value we are curious about, and t prime is a specific time in the future.
Got it. So the semicolon is essentially the wall between the present and the future.
That's a good way to look at it.
If we are translating this entire function, this p of y, ty prime, t prime, into a plain English question, what is it actually asking us?
In plain English, this function is asking, what is the exact probability that our stock price will land in a specific neighborhood around phi prime at a future time prime, given the absolute stone-cold fact that it is currently sitting at value y at time t?
Given the fact that it started at y, that's the anchor point.
Yeah.
We know our current reality. We just want the odds of a specific future reality.
Yes, it is a conditional probability. It connects a known present to an unknown but probabilistically quantifiable future.
Okay.
But before we can really use this tool, we have to confront a limitation in the model we've built so far.
Right, because our model is currently built out of those rigid little steps we talked about.
Exactly. The trinomial random walk is a discrete model. Time only moves forward in rigid chunks of delta t. The price only moves up or down in rigid blocks of delta y.
Yeah.
But real financial markets don't operate like an 8-bit video game.
They don't just sit frozen for exactly 1 second and then suddenly teleport a penny up or a penny down.
No, they flow. Information is being digested continuously. Millions of algorithmic trades are executing every microsecond. To model reality accurately, we need to transition from a discrete, blocky model to a continuous, fluid model.
We need to upgrade from 8-bit graphics to high definition.
Exactly. We need our time steps, the delta t, and our value steps, delta y, to become infinitesimally small. We need to shrink those rigid steps until the jagged staircase smooths out into a perfect, continuous curve.
Okay, mathematically, how do we force this transition? We have this transition probability density function, this tool for understanding where the price might go. But if the market is a fluid moving target, we need equations that govern how that probability flows over time.
And this requires us to build some differential equations. We'll start by looking forward. We want to figure out how our variable arrives at that specific future target y prime at the future time t prime.
Okay, let's set up the logic for this. I'm visualizing the finish line. We are standing at the future time t prime, and we're looking at the exact bullseye value of y prime.
Now, step backward in time, just one single microscopic tick. We are now at time t prime minus delta t.
Okay.
According to the strict rules of our three-pronged fork model, how could the price have possibly landed dead center on the bullseye prime on the very next tick?
Well, looking at our fork, it had to come from one of the 3 immediate prior states. There are only 3 launch pads that can reach the target.
Walk us through them.
Launch pad 1. The price was sitting slightly above the bullseye at y prime plus delta y. From there, it had to take the downward path to hit the target.
Correct.
Launch pad 2. The price was sitting directly on the bullseye already at y prime. From there, it had to take the flat path, doing absolutely nothing to stay on the target.
Yes.
And launch pad 3, the price was sitting slightly below the bullseye at y prime minus delta y. From there, it had to take the upward path to hit the target. Those are the only 3 physical ways to arrive at y prime at time t prime.
That physical logic maps directly into a mathematical equation. The total probability of being on the bullseye right now is just the sum of the probabilities of being on each of those 3 launch pads a moment ago, multiplied by the chance of making the correct jump.
So the probability of hitting the target equals the chance you are above it multiplied by alpha, which is the chance of jumping down, pLs, the chance you were already on it, multiplied by 1 minus 2 alpha, the chance of staying flat.
Right.
PLUS, the chance you were below it, multiplied by alpha, the chance of jumping up.
Exactly. That is a perfectly sound, discrete equation. But remember, we want to upgrade to high definition. We want everything to be continuous and smooth.
Right.
To make that happen, mathematicians use a heavy-duty tool called the Taylor series expansion.
The Taylor series. Okay, whenever someone says Taylor series, my instinct is to run the other way.
It scares a lot of people.
Let's see if we can build an intuitive analogy for what this tool actually does, rather than getting bogged down in the calculus.
I think an analogy is exactly what we need here.
Okay, tell me if this works. Is a Taylor series essentially a way to predict the future shape of a path by intensely studying the local behavior of that path right now.
Hmm.
For example, imagine I am driving a car down the highway, blindfolded, and you are in the passenger seat. You want to mathematically predict exactly where the car will be in 5 seconds.
Okay, I'm terrified, but I'm with you.
You don't have a map of the highway. All you have is the dashboard and my steering wheel. A Taylor series says you don't need the map. You just need to know my current position.
Yeah.
That's piece one.
Right.
Then you look at the speedometer, my current velocity. That's the first derivative.
Yes.
Then you feel how hard I'm pressing the gap pedal, my acceleration. That's the second derivative.
Okay.
Then you look at the angle of my steering wheel, the curve of the path. If you sum up all those local, immediate pieces of information, you can project a highly accurate curve of exactly where the car is going to go.
Okay.
Is that what a Taylor series does to an equation?
That is a phenomenal analogy. Yes. A Taylor series takes a function and breaks it apart into an infinite sum of its derivatives. Its velocity, its acceleration, its curve all calculated at one single point. It allows you to approximate the value of a function at a nearby point using only local information.
So we take this Taylor series tool and we apply it to our chunky, discrete probability equation. We expand the probabilities of being on those 3 launch pads.
We do. We expand the probability of being slightly above the target, slightly below it, and slightly before it in time. We write them all out as these long series of derivatives. And when you substitute all of that back into our main equation,
It must look like an absolute nightmare on the chalkboard.
Right,
Just a
right.
chaotic mess of symbols.
it looks horrifying for about 3 seconds. But then the most beautiful thing in algebra happens. A massive cascading cancellation of terms.
Mathematical spring cleaning.
Exactly. Think about our probabilities. We have a chance of jumping up alpha and a chance of jumping down alpha. When you expand these with the Taylor series, the terms related to the upward jump have positive signs, and the terms related to the downward jump have negative signs. Because the probabilities are symmetrical, they literally annihilate each other. The positive velocity cancels the negative velocity.
So vast chunks of this horrifying equation just quietly vanish.
They vanish entirely, and after the dust settles, we are left with a surprisingly elegant, stripped-down equation, but it's still technically discrete. We have to take the final step to make it truly continuous. We have to take the continuous limit.
Right. This is where we take our chunk of time, delta t, and our chunk of space, delta y, and we shrink them down toward absolute zero.
But here is where we hit a profound physical constraint. If you shrink space and time down to zero, you have to be incredibly careful about the speed at which you shrink them relative to each other.
Why? What happens if we mess up the ratio?
Think about the random walk. The particle is taking a step of size delta every delta t seconds. If you shrink the space, the delta y, to zero very fast, but you leave time, delta t, relatively large, the particle effectively stops moving.
Oh, because the steps are too small to matter.
Right. It takes zero-size steps, the model collapses, nothing happens.
Okay, so that's no good. What if we shrink time to zero really fast, but leave the step size large?
Then the particle is taking massive steps in zero time. It's moving infinitely fast, it teleports, the math blows up to infinity, and again, the model collapses.
So it's a Goldilocks problem.
Eh,
Space and time have to shrink at the exact perfect ratio to keep the model stable.
Precisely. And when we look at our freshly cleaned up equation, we see this exact ratio sitting there. The term is alpha multiplied by delta E squared, all divided by delta 2.
Alpha delta E squared over delta T.
Yes, for the mathematics to survive the continuous limit to neither freeze nor explode, this specific ratio must equal some finite non-zero constant. It's a speed limit for the random walk. We define this constant as c squared.
So we declare that this cluster of shrinking variables is perfectly balanced, and we just call that balance c squared.
Yes. And the moment we lock in that c squared, the transition is complete. We arrive at our final continuous equation. I'll read it out.
Go for it.
The partial derivative of p with respect to future time t prime equals c squared times the second partial derivative of p with respect to future value y prime squared. Or partial p over partial t prime equals c squared partial squared p over partial y prime squared.
Okay, let's take a breath. We have arrived at our first major partial differential equation. This is a big moment. What is this equation actually telling us about reality?
This equation is a titan in applied mathematics. It's known as the Fokker-Planck equation or the forward-Kolmogorov equation. More broadly, it is a diffusion equation.
Diffusion, like when you drop a single bead of red ink into a glass of still water, and you watch it slowly spread out and cloud the water.
That is the exact physical process this math describes, except instead of ink spreading through water, it describes how probability spreads through time. Yeah. When you start, you know exactly where the price is. The probability is a single concentrated drop. But as time moves forward, that certainty diffuses. It spreads out.
And what about that constant we just defined, that c squared, that balanced the equation? What does that represent in the real world of finance?
That is the most crucial part. In finance, the quantity C is directly related to volatility.
Volatility, the wildness of the market, how violently prices are swinging.
Yes. Look at the equation. C squared is the multiplier on the right side. The larger C is, the faster the probability diffuses. If volatility is high, the ink spreads incredibly fast. The range of possible future prices explodes outward.
Makes sense.
And if volatility is low, the ink spreads very slowly. You have much more certainty about where the price will be.
That is incredibly elegant. So, to summarize this whole journey so far, the forward equation projects our present reality into the future, showing us how uncertainty spreads like ink in water, driven entirely by the volatility of the market.
Perfectly stated.
Okay, but what if we want to flip the script? The forward equation tells us where we might go. But what if we already know exactly where we need to end up?
Okay, give me an example.
Say you're a hedge fund, and you have a derivative contract that only pays out if the stock hits exactly $100 at midnight on Friday. You know the target. You want to know the odds of hitting that target from your current position today.
Oh. For that, we can't look forward. We have to run the mathematical tape in reverse. This brings us to the backward Kolmogorov equation.
The backward equation. Okay, conceptually, how does this differ from what we just did?
In the forward equation, we use the future variables t prime and y prime as our independent variables. We were asking, how does the future change? In the backward equation, we fix the future target. The target is locked.
Okay, target lock.
Instead, we use our current state variables, t and y, as the independent variables. We are asking, if I change my current position, how does that change my odds of hitting the locked target?
Okay, this is where we need another deeply intuitive analogy, because backwards time travel in calculus is hard to visualize. And I have to say, the analogy used by the author of the CQF lecture notes here is absolutely brilliant. It's highly specific, a little bit cheeky, and it clarifies the logic perfectly. Let's map it out.
Let's hear it.
Imagine your timeline for an evening. We start with an initial state. It is 7 p.m., and you are sitting at your desk in the office. That is our point y, t. Current value, current time.
Okay, 7 p.m. at the office.
Then we move forward 1 hour to an intermediate state. It's 8 p.m. And just like our trinomial walk, you have 3 distinct choices of where you could be.
3 paths.
Right. Path 1, you could go to the pub. That represents moving up to I plus delta I. Path 2, you could stay working late at the office. That represents staying flat at the hay. Or path 3, you could go to a place the text specifically names as Madame Jojo's, which we will say represents moving down to A minus delta Y.
A classic 3-pronged fork in the road at 8 p.m.
Exactly. And then we have the final state, the locked target. At midnight, regardless of what happened earlier, you must be safely tucked up in bed. That is our future point James C. Elf, D prime.
So we have the 7 p.m. starting line, the 8 p.m. branching paths, and the midnight finish line. Let's trace the probabilistic logic. The total probability of getting from your office desk at 7 p.m. into your bed at midnight is essentially the combined sum of 3 distinct separate journeys through the evening.
Let me trace them out. Journey 1. The probability that you take the upward path to the pub at 8 p.m. multiplied by the probability that, starting from the pub, you eventually make it to bed at midnight.
Yes. Journey 2. The probability that you stay flat at the office at 8 p.m. multiplied by the probability that, starting from the office at 8 p.m., you make it to bed at midnight.
And Journey 3. The probability you take the downward path to Madame Jojo's at 8 p.m. multiplied by the probability that, starting from Madame Jojo's, you make it to bed at midnight. You sum those 3 complete journeys together, and that gives you your total odds.
Precisely. Now, what is conceptually vital here is what we don't care about. What happens between 8:01 p.m. and 11:59 p.m. is completely irrelevant to formulating this specific equation step.
We don't care if you left the pub, went to a diner, caught a cab, and lost your shoes.
We don't care about the intermediate noise. We are only concerned with linking the immediate next step, the 8 p.m. locations, to the ultimate target state bed at midnight. We are defining the total probability based on the probabilities of the remaining legs of the journey.
Okay, that logic is ironclad. It makes perfect sense. But if I apply the exact same heavy-duty math to this new pub-to-bed equation, if I expand everything with the Taylor series, cancel out the symmetrical up and down jumps, and take the continuous limit shrinking time to 0, does it just spit out the exact same diffusion equation, but backwards.
It gives you something remarkably similar, but with one critical defining difference. When the mathematical dust settles on the backward equation, the result is this. Partial p over partial t plus c squared partial squared p over partial y squared equals 0.
Let me compare that in my head. Partial p over partial t plus c squared partial squared p over partial y squared equals 0.
Look at the structure. It is almost identical to the forward equation, but with a sign change.
Oh, I see it.
In the forward equation, the time derivative and the spatial derivative are on opposite sides of the equal sign, balancing each other. Here, they are on the same side, separated by a plus sign, summing to 0.
A single plus sign instead of an equal sign.
Yes, and in the world of differential equations, that single sign change alters the entire fundamental nature of the mathematics. It flips the flow. It turns a forward diffusion equation into a backward diffusion equation. It means the equation must be anchored by a known boundary condition in the future, the bed at midnight, and solved backwards through time to the present.
It is wild that flipping one mathematical symbol completely reverses the flow of time in the model.
It is a beautiful symmetry. However, we have to acknowledge a reality check here. This elegant symmetry, just flipping a minus to a plus, only works perfectly because our foundational trinomial random walk was so incredibly simple and symmetrical.
Right, because we assumed going up was just as likely as going down.
Exactly. If we were to look at more complex, realistic random walks, where maybe the price has a tendency to drift upwards, or where the volatility changes depending on how high the price is, the forward and backward equations get vastly more complicated. The relationship between them is no longer just a simple change of a minus sign. The elegant mirror shatters.
The messy reality of the real world always ruins the pristine math eventually.
It does, but for this foundational understanding, we stick with the pure model.
Okay, so let's assess where we are. We have successfully built the engines. We have two partial differential equations, or PDEs. The forward equation to predict the spread of the future, and the backward equation to calculate the odds of hitting a target. But building the engine and driving the car are two different things. How do we actually solve these PDEs to get a usable number?
Well, here is the harsh truth of quantitative finance. As a general rule, nobody spends time finding explicit, manual algebraic solutions to these complex PDEs.
Because they are notoriously mind-bendingly hard to solve.
They are. In the real world, quants rely on raw number crunching. They use supercomputers to brute force the math using numerical methods and grids. Modern finance runs on silicon, not chalkboards.
So why bother looking at the equations at all?
Because there's immense value in solving a simplified case manually. By forcing ourselves to solve this pure equation, we uncover a genius mathematical technique, a shortcut that applied mathematicians use to untangle the unsolvable.
Okay, I love a good mathematical magic trick. How do we solve an impossible PDE without a supercomputer?
The fundamental problem with our PDE is that it depends on two independent variables. It depends on time, t prime, and value, high prime. Imagine trying to map a landscape where both the longitude and the latitude are constantly stretching and shrinking independently of each other. The calculus becomes an absolute mess.
It's like trying to juggle with two hands while walking on a tightrope. Too many variables are moving at once. You want to simplify the performance.
Exactly. You want to turn the juggling act into a one-handed trick. And the way mathematicians do this is by looking for what are called similarity solutions.
Similarity solutions, what does that actually mean?
It means we abandon the search for a general, all-encompassing solution. Instead, we hunt for a specific, simplified family of solutions. We make a highly educated guess that our probability function p takes a very specific, weird-looking mathematical format.
Let me make sure I have this format exactly right. We guess that p is equal to our time variable t prime raised to the power of some unknown constant a, and that is multiplied by a function of a fraction e prime divided by t prime raised to the power of some unknown constant b. So p equals t prime to the a times f of y prime over t prime to the b.
That is the exact ansatz, the educated guess.
Now, wait a minute. Let me push back here. I am looking at this guess. We just get to invent a bizarre combination of variables, conjure two random constants a and b out of thin air, and force it into the equation? That feels like cheating. And more importantly, how do we even know what a and b are supposed to be?
It absolutely feels like cheating. It is one of those leaps of intuition that makes applied mathematics an art form. We are betting that the chaos of the two variables can be organized into a specific structure. And finding the true values of A and B is the real detective work of this entire process. We don't just guess them, we mathematically corner them until they reveal themselves.
Okay, let's play detective. Let's corner these constants. The whole goal of this weird format is to squish our two annoying variables, time and value, into just one single unified variable.
Yes. We introduce a brand new variable, which we'll call the Greek letter 11, and we define ISI as the messy fraction inside the parentheses, e equals y prime over t prime to the b.
Okay, ESI equals y prime over t prime to the b.
By doing this, our goal is to substitute A into our complex partial differential equation and hopefully watch it collapse into a much simpler ordinary differential equation, or ODE. And ODE only has one independent variable. It's a one-handed juggling trick, much easier to solve.
But for this collapse to actually work, we have to find the perfect value for b. How do we hunt down b?
We take our guessed function, p, and we violently plug it back into the original Fokker-Planck equation. We calculate the partial derivatives.
Okay, let's walk through the mechanics of that conceptually.
The original equation has two sides. The left side is the time derivative, how the probability changes as time changes. The right side is the spatial derivative, how it changes as the price changes. When we substitute our new c variable into the left side, the time derivative, the rules of calculus pull down a factor of time from the exponent. Because phi divides by t prime to the b, taking the time derivative pulls out a factor of t prime to the power of -1.
Okay, so the left side spits out a rogue time variable.
Now we look at the right side. The right side requires us to take the second spatial derivative we derive with respect to y prime twice. Every time we take a derivative with respect to y prime, the chain rule pulls out the denominator of our c fraction, which is t prime to the -b. Since we do it twice, we pull out t prime to the -2b.
So the right side spits out a rogue time variable with a power of -2b.
Exactly. Now here is the absolute logical trap we spring on the equation. For our similarity solution to work, the final equation must only depend on ekla. The rogue time variables t prime must completely cancel out and disappear.
If one side of the equal sign has time left over and the other side has a different power of time left over, the equation is broken. They must match perfectly so they can be divided out.
You've nailed it. For the time variables to cancel out, the power of time on the left side must equal the power of time on the right side. The left side gave us a power of -1. The right side gave us a power of -2b. Therefore, -1 must equal -2b.
-1 equals -2b. The algebra is inescapable. If you divide both sides by -2, you get b equals 1 over 2, or 1/2.
The math physically forces b to equal 1/2 to balance the temporal and spatial dimensions of the diffusion. We didn't guess b. The structure of the universe demanded it.
That is incredibly satisfying. The exponents balance the equation. Okay, one constant down. We know b equals 1/2. What about a? How do we corner a?
Finding an A requires us to step away from calculus for a moment and remember the physical reality of what we are actually modeling. What does P represent?
P is the transition probability density function. It is probability.
Yes, and we discussed the golden, unbreakable rule of probability earlier.
All possible outcomes must sum to exactly 1 or 100%.
Right. In the language of continuous calculus, summing all outcomes means taking an integral. The total area under our probability curve, stretching from -infinity to +infinity, must equal exactly 1.
The area is 1,
Yeah.
always.
So we take our guessed function, p equals t prime to the a times f of 11, and we set its total integral equal to 1. But to actually calculate this integral, we have to change the variable of integration from the real-world price y prime to our invented variable 11.
Okay, a substitution in the integral.
When you do a substitution like that in calculus, it forces a scaling factor to pop out. It's related to the Jacobian. Because y prime equals y times t prime to the 1/2, when we swap the variables, an extra t prime to the 1/2 pops out in front of the integral.
So now we have t prime to the a from our guess multiplied by t prime to the 1/2 from the substitution sitting in front of an integral that must always equal 1.
Exactly. Now think about the logic. Time, t prime, is constantly moving forward. It is always changing. But the integral must always equal exactly 1, regardless of what time it is. The probability can't suddenly become 105% just because an hour passed.
The only way a changing variable can equal a constant 1 is if that variable effectively disappears. And the only way a variable disappears in algebra is if its exponent is exactly 0, because anything to the power 0 is 1.
Brilliant. We have a t prime to the a times t prime to the 1/2. When you multiply terms with the same base, you add the exponent. So we have t prime to the power of a plus 1/2. For this to equal 1 at all times, the exponent a plus 1/2 must equal 0.
And if a plus 1/2 equals 0, then it must equal negative 1/2.
The conservation of total probability mathematically forces a to be negative 1/2. We've cornered our second constant.
That is phenomenal. So by using the structural balance of the equation, the physical laws of probability, we found b equals 1/2 and a equals negative 1/2. We have our similarity solution parameters.
We do. And, armed with a and b, our terrifying partial differential equation, the two-handed juggling act, collapses. The time variable is entirely eliminated. It simplifies down into a highly manageable ordinary differential equation. It becomes negative 1/2 times I times f of xi equals c squared times df over d at y.
Okay, negative 1/2 f of psi equals c squared df d at y. It's still calculus, but it looks a lot less scary. It's just a single variable xe relating to its own derivative.
It is much less scary. In fact, this is an equation that a first-year calculus student can integrate step by step. You separate the variables, put all the xi's on one side and all the f's on the other, and integrate. Integrating 1 over f gives you a natural logarithm.
To get rid of a natural logarithm, you exponentiate both sides.
Exactly. You raise e to the power of both sides, and when you do that, you arrive at the final shape of our function. The function f of xi equals a scaling constant a, multiplied by the exponential of negative c squared over 4c squared.
Okay, we made it. We survived the deep math. We started with a three-pronged fork, expanded it to infinity, shoved it into a PDE, squished it with a similarity solution, and integrated it. And we are left with a times the exponential of negative c squared over 4c squared. But I have to be honest, it still just looks like abstract math. It doesn't look like money or finance or probability yet.
It doesn't, because it's still written in our fake, invented variable 11. To see the real magic, we have to translate it back into the real world.
This brings us to the grand reveal.
The grand reveal. Let's do the translation.
We take our final function, and everywhere we see a c, we swap our original variables, y prime and t prime, back in. Remember, ci equals y prime over the square root of t prime, and we plug in the constants a and b we found. When you do all the algebra, the final real-world equation for our transition probability p is this p equals 1 over 2c times the square root of pi to prime, all multiplied by the exponential of negative y prime squared over 4c squared t prime. Let me repeat that slowly, and look at the structure. P equals 1 over 2c times the square root of pi t prime times the exponential of negative y prime squared over 4c squared t prime. Wait. The structure of the fraction out front, the negative variable squared in the exponent. I recognize this. Anyone who has taken a basic statistics class should feel their ears burning right now.
It is the most famous curve in mathematics.
This maps perfectly, symbol for symbol, to the probability density function for the normal distribution. This entire journey, from chaotic coin flips to high-level calculus, just spat out the formula for the bell curve.
Exactly. The bell curve. Think about how profound that is. We didn't assume the market followed a bell curve. We started with the dumbest, simplest assumption possible. A price can jump up a cent, jump down a cent, or stay flat. We extrapolated that microscopic noise to infinity using pure logic, and the natural, inevitable mathematical result that materialized is the perfect symmetrical geometry of the normal distribution.
That genuinely gives me goosebumps. It is like looking at a pile of random sand grains and realizing they naturally arrange themselves into a perfect pyramid. The chaos creates order. Let's spend some time really analyzing this bell curve. What is this equation explicitly telling us about our future stock price?
It gives us 3 concrete mathematical facts about the future. Fact 1, the variable pi prime, the future value of our financial instrument, is normally distributed. The probabilities map to the bell shape.
Okay, fact 1, it's a bell curve. Fact 2.
Fact 2, it has a mean of 0.
Meaning the absolute highest point of the bell curve, the single most likely outcome, is perfectly centered exactly where the price started. The peak of the mountain hasn't drifted left or right.
Right. Because our foundational model assumed equal probability of going up or down, the most mathematically likely outcome is that the up jumps and down jumps cancel out, leaving you exactly where you began. And fact 3 is the most important for finance. It has a standard deviation of act times the square root of 2t prime.
Standard deviation. In layman's terms, standard deviation is the width of the bell curve, how fat or how skinny it is.
Yes, it is the measure of uncertainty. A skinny curve means you are very certain where the price will be. A fat curve means the price could be almost anywhere.
And look at the ingredients that make up that standard deviation with the c times the square root of 2t prime. We have c, which we know is volatility. And we have 2 prime, which is time.
So the width of the curve, the sheer amount of uncertainty in the market, is directly driven by how volatile the asset is, multiplied by the square root of how long you have to wait.
Let's visualize this happening in real time. Imagine an animation of this bell curve.
Picture the graph. The x-axis is the price. The y-axis is the probability.
Let's say we look at time equals 0.25 relatively soon after we start. What does the curve look like?
Because time t prime is small, the standard deviation is small. The bell curve is incredibly narrow, and its peak shoots high into the air.
The probability is tightly clustered around the starting price. High certainty.
Exactly. Now let time run forward. Time equals 0.5, further into the future.
The dat prime variable gets larger, which means the standard deviation gets larger. The bell curve shrinks in height, like a balloon losing air, and the base flattens and widens out.
The probability is diffusing, spreading out.
And at time equals 1, even further out, the curve is even flatter and even wider. The peak is much lower, and the tails stretch way out into the extreme prices.
This is the ultimate mathematical truth of forecasting. The direct relationship between time, volatility, and uncertainty. As time moves forward, the variance inevitably grows. The longer you wait, the wider the range of possible outcomes, and the less certain you are of any specific reality. Time literally causes uncertainty to spread like a gas expanding to fill a room.
We've built it. We've taken discrete, chaotic coin flips and transformed them into the elegant, predictable, continuous geometry of the bell curve. We have built a machine that perfectly quantifies risk. It feels like a massive triumph. We've solved the market. We have the map.
We do have a beautiful map, but this is where I have to step in and be the pragmatic buzzkill.
I knew it was too good to be true.
As elegant and mathematically sound as this model is, we have to look beyond the trinomial walk. We have to generalize for actual finance, because this perfectly solved bell curve equation has some catastrophic limitations when you try to apply it to the messy real world.
So why can't a hedge fund just plug this beautiful pie and equation into their computers and get rich? Where does the model break reality?
The primary issue is how naive our random variable y is. Financial quantities are far more stubborn than pure math. The first major flaw is known as the zero bound.
The zero bound. Explain how the bell curve violates that.
Look at our mathematical model. The variable y can wander infinitely in either direction. A normal distribution bell curve stretches from negative infinity to positive infinity. It assigns a probability, however small, to every number on the number line.
Okay, but think about real equity prices, a share of Apple or Microsoft.
Exactly. A stock price cannot go below zero. The absolute floor of a company's stock is $0, at which point the company is bankrupt and ceases to exist. A share cannot be worth negative $10. You cannot owe someone money for owning a stock.
But our elegant bell curve model doesn't know that. If a stock starts at $5 and has high volatility, the bell curve will flatten out so much that a massive chunk of its probability will spill over into the negative numbers.
It will. The model might confidently predict that there is a 15% chance a stock price will be negative $20 next year. It is predicting a physical impossibility. Therefore, a pure normal distribution is fundamentally flawed for modeling equities.
That is a massive structural hole in the map. What else breaks?
Well, think about different types of financial instruments. Equity stocks might just wander aimlessly until they hit zero or infinity. But what about interest rates, the rates set by the Federal Reserve?
Interest rates behave completely differently. They don't just wander to infinity. If interest rates hit 50%, the entire global economy collapses.
Precisely. Central banks actively intervene to control them. So mathematically, interest rates exhibit what is called mean reversion.
Mean reversion, like they're attached to a rubber band.
Exactly like a rubber band. They might wander randomly for a bit, but there's always a gravitational pull dragging them back toward a long-term historical average. A simple trinomial random walk has no rubber band. It has no memory and no gravity. It just wanders blindly. So to model an interest rate, you need an entirely different equation that factors in that elastic pull.
So if we realize our map is flawed and we try to fix it, if we try to generalize the random walk to build in a hard floor at zero, or to attach a mathematical rubber band for mean reversion, what happens to all that beautiful, elegant calculus we just did?
It gets incredibly messy very fast. When you generalize the random walk to include these real-world constraints, the forward and backward Kolmogorov equations become vastly more complex.
And what about that beautiful symmetry we found, where the backward equation was just the forward equation with a minus sign flipped to a plus sign?
That is the first casualty. With more complex, generalized walks, the relationship between forward and backward time is no longer a simple sign change. The equations warp. The elegant simplicity we discovered today completely shatters.
Wow, that is a humbling realization. The math is perfect, but the reality is messy. The map is beautiful, but the territory is a swamp.
It is humbling, but it perfectly sets the stage for the true discipline of quantitative finance. What we explored today is the bedrock. Quants spend their entire careers trying to patch the holes in this very model, building increasingly complex equations to capture the zero bounds, the rubber bands, and the chaos of the real world.
Let's pull all of this together and distill the massive journey we just went on.
It was quite a journey. We covered a lot of ground.
We started with the simplest possible assumption, a discrete, three-path random walk, a trinomial fork in the road. We then used the brilliant local projection logic of the Taylor series to bridge the gap from chunky, rigid steps to smooth, continuous, flowing time.
From there, we derived the heavy-duty partial differential equations, the forward equation to watch probability spread, and the backward equation to calculate the odds of hitting a specific target.
We then pulled off a mathematical magic trick. We used similarity solutions, squishing time and space together, forcing the exponents to balance at 1/2 to turn impossible PDIs into solvable ODs.
And miraculously, out of all that intense algebraic maneuvering, the universe handed us the normal distribution bell curve, the ultimate mathematical translation of pure randomness.
The key takeaway for you, listening right now, is how incredibly powerful this underlying logic is. We have just explored how incomprehensibly complex natural phenomena like the wild volatility of a global financial market moving through time can be elegantly captured and described simply by understanding local, microscopic, step-by-step behavior and scaling it up to infinity. You don't need to know the whole route to map the highway. You just need to understand the steering wheel.
It is the triumph of applied mathematics, finding the hidden structure inside the chaos.
It truly is. But as we wrap up this deep dive, I want to leave you with a final, slightly provocative thought to ponder. A thought that builds directly on the philosophical shift we made at the very beginning of this journey.
I love a good puzzle to end on. What are you thinking?
Early on, we established that predicting a single deterministic financial path is literally impossible. We abandoned the exact prediction. So instead, the brightest mathematical minds on Earth chose to model the probabilities perfectly. They built the bell curve. They mapped the forest instead of the tree.
Right, they built the model we just explored.
But here is the paradox. What happens when the model becomes universally accepted? If every single quantitative analyst in the world, at every major investment bank, every hedge fund, at every trading desk, is using these exact same probability distributions, these exact same diffusion equations to price their derivatives, to manage their risk limits, and to program their automated trading algorithms, what happens to the market?
That is a fascinating thread to pull.
Does the mathematical model itself start to dictate how the real-world market behaves? If everyone believes the bell curve is true, and everyone buys and sells according to the rules of the bell curve, does the market fundamentally change to fit the math?
It's the concept of reflexivity. The observer influences the observed.
Exactly. To go back to our opening metaphor of the map, we know the real city is chaotic and shifting. But when every single person in the city is navigating using the exact same flawed blueprint of Elm Street, does the city eventually just rebuild itself to match the rigid black lines on the paper? Does the map eventually become the territory? It's something to chew on next time you see a stock market ticker endlessly scrolling by. Thank you for joining us on this deep dive into the architecture of randomness.